Okay, good afternoon and welcome to the CERIAS Computer Security Seminar here at Purdue University. Our speaker today is a senior PhD student. His advisor is Elisa Bertino, Nabil Mohammed, and his topic today is privacy-preserving attribute-based group key management. Nabil?
Thank you for the introduction. So, as Randy mentioned, I'm going to present this part of my thesis work. I try to avoid technical details as much as possible and try to give a high-level view of what we have done. And so the work I presented it from 3 conferences. I combined them together in a logical order so that it will fit into 50 minutes. And it's joint research work with Ning Shang, who is a researcher at Qualcomm, and my academic advisor, Professor Elisa Bertino. So initially, I'll give you the motivation behind our work and some background information. So are all of you from like computer science background, right? Are there any undergrad students here? So most of them are graduate students, right? Okay. So if you look at all this, the data used to reside in the organization, and access to the data is controlled by the organization itself through various access control mechanisms or through perimeter security. But the picture has changed now. We are now in the cloud computing era where the data no longer resides inside the organization. Now data is moved to the cloud. It provides many benefits, as you already know, but if the data is of sensitive nature, the typical approach to store this data in outside of the organization is to encrypt them. So what the organization does, for example, if it is a hospital, they encrypt the data and upload it to the cloud and give the corresponding keys to the users. Whoever has correct keys can download the encrypted documents and see what's encrypted. So when we talk about encrypted data, one of the key issues with encrypted data is access control. How do you provide access control on encrypted data? For example, in that picture, we had 3 users, Bob, Alice, and Tim. So Bob is a doctor, and he has access only to medical records. And Alice is a nurse. She has access to only clinical records. So how do you make sure that Alice does not access these medical records? So the typical approach that we use in order to do this one is to use selective encryption, where we encrypt different types of documents with different keys and give the corresponding key to the relevant users. So in this case, Alice will get key 2, and Bob will get the first key. Since Alice doesn't have the first key, she won't be able to decrypt this medical record. She will only be able to decrypt these clinical records. So in order to provide selective encryption, one of the critical decisions that you have to make is what kind of a crypto system that you should use in order to realize this. There are 2 main choices. Either you could use public key cryptography, or you can use symmetric key cryptography. So in the coming slides, I'll explain to you 3 most popular PKC systems, public key cryptography systems, and point out their limitations, and then argue why they are not suitable for the scenarios that we are discussing. And we make the case where symmetric key cryptography systems provide a better solution. And if you were present here 2 weeks ago, they presented a system based on public key cryptography. I'll basically touch on that one, lightly touch on that one as well. So the first, as everyone familiar, the traditional PKI, where you have a certification authority which issues certification authorities like VeriSign, which issues public-private key pairs to each and every user. So in this case, each user will have a public-private key pair. The hospital will encrypt the data using the public key of the users and upload it to the cloud. And the users will download the encrypted documents, they encrypted with their public keys, and decrypt it using the private key. They won't be able to decrypt the data encrypted with others' public keys because that doesn't match with their private key. So, do you see any problems here? Any limitations? And if you have any questions, I would like you to ask questions from me so that I know at least you understand some part of the talk. So here one of the major limitation is, if you noticed, here I have to do duplicate encryptions. See, I have the same document. In order to allow different users to access the same document, I need to encrypt it multiple times. So that's duplicate encryption. And another limitation which is not visible from this example is it's very difficult to provide very fine-grained encryption using public key cryptography because it doesn't have that mechanism built in. And as we all know, another limitation is the revocation. Certificate revocation is a big problem in PKI. So the next one, so attribute-based encryption. Are you guys familiar with attribute-based encryption primitive? Right, so it's relatively new compared to PKI, which's been around for about 4 decades. This one was introduced only in 2005. The basic idea here is, instead of having these public key certificates, we use the attributes of user. For example, your email address, or it could be the role that you play as a student. Your role is student, could be an attribute. So those attributes are used as public key, and then whoever want to encrypt something, use those attributes and encode that in the encrypted document. And if you have the corresponding private keys for those attributes, you can decrypt the documents. So here, the users have the attribute doctor, nurse, and doctor. So there are 2 doctors and 1 nurse. So instead of doing duplicate encryption, here we do attribute-based encryption. In this case, the hospital will encrypt once for the attribute doctor, and it will encrypt the clinical records once for the nurses, and will upload it to the cloud. And then the users, Bob and Doctor, who plays the role doctor, can download these encrypted documents, and use their private key, which is derived from their attribute, and consume these documents. So this does have the advantage that there is no duplication, and it does provide very fine-grained access control because it's based on attributes. But this system also has a big problem, namely revocation. When you want to say, if this user is, say, laid off, he is no longer part of the hospital, so you need to prevent that user from accessing the content. In order to do that one, you will have to update the private keys given to other users as well. Private keys given to other users who play the same role as him. For example, Tim plays doctor here. So we need to update the private keys given to all the doctors. If you have many doctors, this is going to be a big bottleneck in the system. So if your system is fairly stable and don't have dynamic updates like adding new users or removing new users, this solution could work. But if you have a fair dynamic system, this solution is going to create a lot of overhead. So the third primitive that I want to talk about this on PKC is proxy re-encryption. And this is the scheme, this is the high-level scheme that the talk 2 weeks ago you presented, the person from the Microsoft. They use proxy re-encryption. So here, the high-level idea is each and every user will have their own public-private key pairs, and the hospital will also have its own public-private key pair. So here, hospital encrypts the data once, it will encrypt each and every document with its public key and give some additional information along with this encrypted document to the cloud. And the cloud use that additional information and convert these encrypted documents into the encrypted documents of the public keys of the users. So in this case, for example, if you take this one, it's originally encrypted with the public key of the hospital. And then using the additional information, the cloud converts that into the public key of Bob and the public key of Tim. So here also, even though the organization doesn't have duplicate encryption, the cloud needs to keep duplicate encryptions. That's a big problem. If you have update to a document, you need to say you cater for 10 users. You will have to re-update it 10 times for all the users. And when you talk about large-scale system, this is going to be a big overhead. And the other problem is this scheme also fails to support fine-grained encryption because it's been proved, theoretically proved that it's an impossibility result to have fine-grained encryption with proxy re-encryption. So in addition to those limitations, the public key crypto systems have these, as you all know, these systems are order of magnitude slower than symmetric key cryptography systems, crypto systems. And as we move along, you will understand it's difficult to provide privacy guarantees with PKC systems as well because of the nature of these public-private key pairs. So having identified these limitations, we propose a system that uses symmetric key cryptography that overcomes most of these limitations and provide much better performance. Although I'm not sharing the performance results. If you look at our paper, you'll see the numbers. So I must warn you that if you use the straightforward use of this PKC, it's also going to have limitations. If you just use the straightforward way, for example, if you use the user-centric way where you give each user a unique symmetric key and use that in your system, that's also going to create limitations. For example, this one will efficiently handle user joins and leave. When the user is laid off, it doesn't going to affect other users because each and everyone has a unique key. But this will have duplicate keys. So straightforward use of PKC is also not going to solve the problem. So another straightforward use is group-centric approach, where users are grouped based on the policies in the system, and for each group you assign a key. So this will solve the problem of duplicate encryption, but it's going to be, it won't solve the problem of handling user dynamic. When one user leaves, you will have to update the keys given to all the users in that group. So we need to be intelligent in order to overcome these limitations. So the ideal solution, we want to have single encryption where we encrypt each document only once, and we want to efficiently handle the user dynamics. When users join or leave, ideally it should not affect the other users. It shouldn't affect the private keys of the users. So the remaining of the talk, I'll try to show you how we try to achieve this ideal solution, at least come close to that ideal solution. So far, do you have any questions? If anything is not clear, please just ask from me. I'm more than happy to answer if you have any questions. So in the next section, I'll be talking about some high-level details about attribute-based system, and then the overall high-level view of our solution. And then I'll talk more details in the next couple of sections. Right. So in an attribute-based system, users are identified by a set of attributes, and same attribute may belong to multiple users. For example, if you take the attribute doctor, it belongs to Bob and Tim, and each user has multiple attributes. And policies are defined based on the attribute conditions. These attribute conditions are formed from the attributes. So this example shows three policies, and depending on the attributes of the users satisfy different policies. And we say that a user becomes a member of this group if the user's attribute satisfies this policy. For example, in order to satisfy this policy, either user need to be a doctor or the user need to be a senior nurse. And these groups could have various relationships. They could be completely disjoint, or they could be partially overlapping, or they could be completely overlapping. So user dynamics. So as the system evolves, there might be new users joining a group or leaving a group. So we call those leave and join operations. For example, even change in one attribute could trigger both. So if you take this one, Bob is a junior doctor, and Bob satisfies this policy. Because of that, he is a member of this group. So as the time passes, he is promoted to a senior doctor. So he no longer satisfies this policy. So because of that, it triggers the leave operation, and he is not a member of that one. And since Bob satisfies now this policy, it triggers a join operation and becomes a member of that group. So now I will present you three key concepts that most of the group key management schemes provide. So the first one is backward secrecy. Usually most of the systems provide backward secrecy. What it means, when a user leaves, say for example the company, we don't want that user to access the content published after that. So this makes sure that user is not allowed to access keys after user is left. And forward secrecy. Forward secrecy makes sure that user cannot access historic data. Some system allows users to access historic data, and some system not. It depends on the application. So another important concept is collision resistance. When you provide this fine-grained group key management based on this attribute, we need to make sure that if individual users cannot derive the group key, they shouldn't be able to combine their attributes and derive the group key. That's what collision resistance means. If they can combine and generate the group key, we say that the scheme is not collision resistant. I'll have an example later on in my presentation about this. So going back to that trivial approach that I mentioned earlier, the group-centric approach where each user is grouped into multiple groups based on the policies, and then assigning keys. So it looks something similar like this. So as I mentioned earlier, it provides single encryption, but it's difficult to manage keys because when you group users, theoretically speaking, there could be 2 to the power n-1 groups, and thus 2 to the power n-1 keys. So that's a huge number of keys to manage. We don't want to do that. And the bigger problem is handling joins and leaves. So for example, if a user happens to leave, a user who's in this intersection happens to leave, you have to update the keys given to all the users here, all the users here, and all the users here. And since these are symmetric keys, the only way to give symmetric keys in a secure way is to establish private communication channel. You need to use public key cryptography to establish secure channels and give the keys. So this is going to be a huge overhead if you have to use this approach. So how can we avoid that? So we make this observation. So even if you don't understand like any other part of the lecture, this is the key message that I wanted to give you, where you don't need to give the keys to the users upfront. You can delay because users need the keys only when they decrypt it. So based on this observation, we do not give the keys upfront to the users, as in the two straightforward approaches. Instead, we give some secrets to the users that allows them to combine with some other information and derive the keys at the time of decryption. So that's the high-level idea behind the whole group key management scheme that I am going to present. Based on this idea, we build on what is called a broadcast group key management scheme, and then we extend that into attribute-based systems. So this is how it looks like. So you have the users, Alice, Bob, and Tim. Initially, they are, say, each user has a single attribute. Let's not worry about multiple attributes here. So each user has a single attribute, and for each attribute, they get a secret from the group controller. And then later on, the group controller wants to allow the users to derive a symmetric key. So for that, it publishes some public information. So depending on some policy, this public information encodes the policy and hides the symmetric key. And whoever satisfies that policy can combine the public information and their secret and get the symmetric key. For example, if Tim does not satisfy this policy, he won't be able to combine this public information and his secret to get the key. So whenever, say, the group controller now decide to change the key, it doesn't need to update the secrets given to the users. It simply update the public information and broadcast it or upload it to a public location. So you don't need to establish private communication channels. You just need to create this public information and put it somewhere public. Whenever users join or leave, same thing is performed. Right, so let me walk you through a simple example how the whole cycle of how it works. So in step 1, users are issued secrets, just like as mentioned earlier. And then, say, now the policy says that only Bob and Tim, so the S3 and S2, the secrets corresponding to Bob and Tim, right? The policy says only Bob and Tim can access the private key. So the group controller creates a public information that encodes, that hides these secrets and the symmetric key inside the public information. And then it uses this symmetric key and encrypts the data and publish somewhere, maybe upload to a public website. And now any user can download this encrypted document and the public information. Now Tim, since his secret is encoded inside that public information, he can use that public information along with his secret to derive the key. But however, Alice, her secret is not inside that public information. She won't be able to derive the secret key. We mathematically prove there is only a negligible probability of deriving the actual key if you don't have a valid secret that's included inside the public information. So only Tim can decrypt it, but Alice won't be able to because she doesn't have the correct key. Right, so that's the high-level idea about the broadcast encryption. I will again give you only the high-level idea of the construction of broadcast key management scheme. There are different constructions that you can make. I'll give you one construction, high-level view of one construction.
Question. Could you go back a couple slides, please, just to the, yeah, right there. How does the system, microphone. How does the system preserve forward and backward secrecy when that public information is not necessarily destroyed whenever you publish new public information? Like, I could keep the public information that allowed me to derive the symmetric key with my secret, and I could keep my secret and access that data at a different time. as long as I have a copy of the data encrypted under that symmetric key.
So if you already have the access to that data, it boils down to the digital right management problem. So it has nothing to do with the key management scheme. So if you already have the access to the previous key and the encrypted document, you necessarily have access to the old document. So in that case, you can't prevent from users accessing old data. But if you have a system where if you can assume that users always get the data and destroy it, in that case, if you want to provide, say, forward secrecy, you not only generate the new key, you will re-encrypt all the documents. That will make sure that whoever is new, assuming that they don't have the previous data with them, when they download it, it will make sure that they can't access the previous document. Oh, so if you want to revoke the rights from Tim, what you do is you remove the secret from here and regenerate the public information and a new key and re-encrypt it using that public information and key and upload it. Because now Tim's secret is not in the public information, Tim won't be able to access it from the new public information. Yeah, if you already have it, it's not actually a security problem. Actually, it's a problem of digital right management. Where if you already have the access to the encrypted document and the old key, there is no cryptographic protocol going to protect it. So now I'm going to give you a high-level view of the construction of this broadcast group key management scheme. And I use a lot of acronyms. Don't worry about them. It's a lot of them. So just try to get the high-level idea. Acronyms, you don't need to. So the broadcast group key management scheme, we abstract it into 5 algorithms. So namely, if the first one is set up, it basically set up some public parameters that we need to use in the scheme. And then the secret generation, where it takes user identity and generates a secret. And key generation, depending on the policy, it takes a set of secrets and generates the public information and the symmetric key. And the public information hides the symmetric key. And key derivation algorithm, which is these users, Tim, Bob, and Alice users, they input their secret and uses the public information and get the key. And so whenever you say the set of secrets changes, it could change due to the policy changes, or it could change due to new users added to the system, or existing users are revoked. So whenever that happens, new public information and a new key is generated. And we published this initial work in ICD 2010, that's about 1.5 years ago. So the high-level idea is, what we do is we get these secrets and create a special matrix. We call this access matrix. And using that access matrix, we get the null space and then the basis of that null space. So, and then what we do is we get a random vector from that basis of the null space and embeds the secret key inside that one. So for an outsider, it's just a random set of numbers. They won't be able to, we prove that an adversary who doesn't have any knowledge about these secrets able to derive the key. We show that it's very negligible. So it generates this special vector, we call it access control vector, and this is the public information. And users who have valid secrets, they can also generate a special vector. We call that key extraction vector. And so the magic here is when they do the inner product of this public information and the key extraction vector, it cancels out everything and gives the key. So this actually there is no magic here because we use the null space. It's perpendicular to the vector that user generates, and it cancels out everything and gives the key out. But if an adversary who cannot construct this vector, they won't be able to derive the key with any significant probability. So, and one thing probably you didn't notice about this one, if you look at the complexity of the public information, the size of the public information, and the complexity of key generation and key derivation algorithm, it's proportional to n. So if you have large number of users, the key generation, key derivation, and the public information that you have to transmit going to be huge. So one of the main things that we try to optimize is how can we make this sublinear in X? How can we make, if you have 1,000 users, can we reduce the size of this public information? Right now, it's going to be 1,000 elements. It's going to be huge if you are to transmit with the encrypted documents. So we used the research results from its previous research result to convert this public information and the other algorithms sublinear in n. So in fact, for these 1,000 users, we make it to 8. We make it logarithm of this number. So what we do is, if you notice, for each identity attribute, I gave a single secret to each user. So instead of giving one secret, what we are going to do is, we give a set of secrets for each identity. And these secrets are given in a way, there are some overlaps. So there are secrets that multiple users share. And there is this technique called subset cover technique, where users are ordered in the leaf of a balanced binary tree, and the secrets are assigned to internal nodes. So when you give users secrets, you give secrets from the leaf node to the root node. And so when you give those secrets, it defines the sharing. And there are techniques, I'm not going to go into details here, you probably can look up in the Google. There are techniques to identify subsets of users based on common secret. And you can revoke a user, simply cut the links between the user and the rest of the tree. So that way, we increase the number of secrets given to the user, but it gives a huge performance improvement in the key generation, key derivation, and the size of the public information. So, any questions? Right, okay. So next I'm going to present the attribute-based encryption. It's a natural extension of this broadcast group key management scheme. Actually, the BGKM, it's used as the basic building blocks here. The idea here is, if you look at the broadcast group key management, it considered the identity of the user. So instead of considering the identity, now we are going to consider a set of attributes of each user. In that way, we can provide a more expressive system. So if you recall, each user has a set of attributes. So in this, the policies are specified using the identity attribute. So for example, here is a simple policy here. This one says, this policy says that the role of the nurse should be nurse, or the level should be greater than or equal to senior. So this policy is satisfied by Bob and Ted, Bob and Alice. But if you look at this policy, it says the role should be doctor and the level should be senior. So if you look at these attributes, only Bob satisfies this one, right? But if you look at the attributes of Alice and Ted, they collectively satisfies this policy. So, the Ted is a doctor, and she has the attribute senior. So they collectively satisfy this one. But a good group key management scheme provides the collision resistance. So since they are individually cannot satisfy this policy, they shouldn't be able to derive the key, even though they collectively satisfy the policy. That's what I meant by the collision resistance property. So This is a very important property when you move into attribute-based systems. Even though different users have different attributes, even though they collectively satisfy it, you should not allow them to access the key because they don't individually satisfy it. So from the user point of view, the only change that we do to the algorithm is, instead of issuing a set of secret to each identity, we issue a set of secret to each attribute. And in our paper, we discuss about 3 variations of this attribute-based GKM. And in this talk, I'll limit myself to the third scheme, which I like most. It's based on a tree. Again, I will give only the high-level details because this is a little complicated, this access tree-based group key management scheme. And it's, as I mentioned earlier, it's based on that the construction that I presented shortly. And it's based on Shamir's secret sharing scheme. So those are the only 2 constructs that we use to construct this scheme. So, and on top of that, we also want to provide privacy. So if you look at the scheme without privacy, what we do. So if say user Tim want to get the secret, he will present his identity attributes to the group controller and will get the secret. So this reveals that user has this credential. So how can we prevent this one? So we observed that if we can preserve the privacy of this secret generation algorithm, we can preserve the privacy of the whole group key management scheme, because this is where the user interact. So if we can preserve the privacy, we can preserve the privacy of the whole system. So what we do is we use a protocol called OCBE, which obliviously gives secrets to the users. So the high-level idea is as follows. So instead of submitting saying that I am a doctor, it gives a commitment. A commitment is a cryptographic construct that hides some identity, some value, but still binds it to the user. And then they execute some zero-knowledge protocols, and at the end of the protocol, the group controller sends an encrypted value, which we call an envelope, to the user. So this protocol ensures that the server group controller does not learn the credentials of the user, but at the same time, user can open that, decrypt that envelope, and get the secret only if his credentials satisfied. For example, if this user tried to fool the group controller by saying I'm a doctor without having the actual credential, he won't be able to decrypt it even though he executes this protocol. So this protocol at the end of the day also ensures that only the correct users can decrypt it and get the secret. This, by the way, it's from a previous research. It's not, we used that result in our work. So now the high-level idea of the whole scheme. So what we do is we get this access control policy, which is specified using this attribute condition, and convert into access tree. For example, this is like a simple access tree, which has 2 internal nodes and 3 leaf nodes. So these internal nodes represent the threshold gates. You can represent any kind of policy using an access tree. It could be any combination of ands and os. Okay, so this one, the threshold, even it could be a d out of m, where threshold says you need to have d attributes out of m in order to satisfy that threshold. If it is an m and gate, it's going to be m out of m. You have to satisfy all the child nodes. And if it is o gate, you just need to satisfy 1 out of the m children nodes. Right, so we construct this access tree, and then depending on the threshold, here it's an O gate, so this is threshold 1. So we associate this polynomial is going to be a constant because it's threshold 1. Here, since it's threshold 2, we construct a unique polynomial of degree 1, and you use it to assign secret. I'm not going to go into detail here. These polynomials are related to Shamir secret sharing. Shamir secret sharing is used to, it's designed to collude, but we use it in a unique way that allow us to prevent collusion. What we do is we use unique polynomial, we assign unique polynomial to each user. So if you have a unique polynomial to each and every user, even if two users have two different attributes, they won't be able to combine and get the correct polynomial because those values came from two different polynomials. And since they cannot construct that unique polynomial, they won't be able to get the secret value. So let's consider this hypothetical policy where this says a senior nurse supporting at least 2 insurance plans can access these medical records. So if you express that in Boolean formula, it's going to look like this. User playing the role nurse and the level senior, and 2 out of 4, it's a threshold policy, 2 out of 4 of these insurance plans. So you can represent that using this access tree. So here, in order to satisfy this node, user need to satisfy this one, and this one. So all the 3, because it's an AND gate. In order to satisfy this one, user only need to satisfy any of the 2 leaf nodes, right? So in the key generation, what we do is we follow a top to bottom approach where we assign the actual group key to the root node, the polynomial assigned to the root node, and then we do a top-down computation, which I'm not going to go into detail. What it does is it propagates this actual group key down to the leaf nodes. So when the key derivation is done, it's done in the reverse order. So users need to discover intermediate values using their attribute values. So if they can come up to the root node, they can derive the group key. So that's the high level idea of it. So looking at the attribute, only Alice satisfies that. And even though Bob and Roy jointly satisfies this one, they can't access it because these are based on unique different polynomials. So that provides collusion resistance. So that's a very high level view of that algorithm. I didn't go into any technical details at all. So we use Lagrange polynomial interpolation inside that one. It's a lot of mathematics. So do you have any questions so far? I have about 5 minutes left. I'll try to give you an example where we use this group key management scheme. Again, it's going to be very high level. It's based on one of the papers we published last year. So storage as a service, it's becoming a popular buzzword, and it's being used heavily as well. So the idea here is there are third parties like Amazon. They provide storage as a service. Any organization, they can use their service and pay for the bandwidth they use. They will upload their files to the cloud, and then the users, whoever have, for example, if it is Amazon, you need to have AWS credentials. Whoever has correct AWS credentials can download those files. So actually, I'm going to use Amazon S3 as the example for this SaaS service part, the server part. Okay, so they have this notion of buckets and objects. The bucket is very much similar to the concept of folders that we have in the normal desktop computers, and the objects are the files. So you can have as many objects inside a bucket as you want. And they do have different APIs that allows you to access these. For example, they have a REST API, and you can also directly use the web front end to access as well. So if you look at the Amazon, how they provide the confidentiality, they only support single user scenario, where they provide a thin encryption client which you can use to encrypt a file and store it in the S3. And then you can ask the same thin client to decrypt it. So in other words, Amazon does not provide any solution to do key management. So what we try to do is we replace this thin client without replacing any other thing that Amazon provide, and try to put that one between the user and the Amazon S3 service. So in that way, you don't need to modify anything to use the system. It could well work with even other services like Microsoft Azure, right? So what we need is we need a multi-user solution where the data owner, for example, the hospital, will do all the key management scheme stuff, and users will transparently read and write data. So let me show you the flow of how the data is organized. So for example, let's say we want to encrypt these hospital records and upload it to the Amazon S3 cloud. So just like the scheme mentioned earlier, users are initially given secrets based on their identity attributes, and then this encryption client execute a group key generation algorithm. That's the same key generation algorithm I mentioned earlier. And based on that one, it will generate that public information and the symmetric key. And using the symmetric key, it encrypts the corresponding documents and uploads this encrypted document and the public information along with that one. So we treat this as metadata. Amazon S3 provides a way to store metadata along with any file. We store that as metadata. And one nice thing we do is we utilize this what is called these bucket policies. They allow you to attach policies to buckets, and this bucket policies you can specify for the whole bucket or any object in that bucket. So we use that facility to make sure you can allow any user. So if you might argue that you can allow any user to download this document because it's encrypted, but if you take the model that Amazon S3 has, they charge you based on the bandwidth that you utilize. So we want to make sure that unnecessary downloads doesn't happen. So in order to control that one, we use these bucket policies. What we do is we create a hash value using this public information and the actual secret keys. So we store this. We have example. I don't have a slide with that one. These policies are very easy to write. So we associate these hash values with each object. So the idea is if a user wants to download something, he need to prove that he can generate the same hash value. If he cannot generate it, we don't allow to download it. So it's sort of like a capability. So what the user does is it downloads, it's initially allowed to download only the metadata. So using the metadata and then using the key derivation algorithm of the attribute-based group key management scheme, it generates the actual key, and then it submits the hash value. So then we check against this bucket policy. Only if it satisfies this bucket policy, it sends the encrypted document to the encryption client, and then it decrypts and shows it to the user. So if you use a public key-based crypto system, you can't provide that facility. And also the privacy. It's difficult to provide privacy because you need to have the knowledge of those public keys in order to provide that. But if you use this kind of a setting, you can not only provide privacy but also limit the download. For example, if you look at the talk two weeks ago, in order to provide privacy, you need to download the whole database if you want to provide that's going to be a huge bandwidth. So in summary, we looked at the public key cryptography and its limitations, and then point out that a better way to do this kind of work is to use symmetric key cryptography. And then I showed you our approach to do this one, the broadcast group key management scheme. And then I gave you a high-level idea of how we extend that into attribute-based systems. And then finally, I showed you how we utilize it in a real system. Okay, that's it. If you have any questions, I would be happy to answer. And it's 5:20. If you want to leave, you may. Any questions? Okay, thank you.